Now the first thing I want to do is really just talk a little bit about some of the overview of some of these structural dynamic modeling techniques. And here you see we have the typical new modal test engineer asking, can you explain modal analysis? And there are so many intricate details that there's a lot that we have to discuss in order for you to really appreciate all these different aspects and understanding how these things are used for solving structural dynamic problems. So what I want to do in this first presentation is try to give a broad brush over the whole experimental modal analysis arena. Now some of these things may not be fully understood at this time, but this is going to be a one broad brush overview of everything that we're going to cover in terms of this course. Now the first thing I want to try to note here is that we talk about systems and we talk about modal analysis and structural dynamics. Now modal analysis is the process whereby we define the dynamic character of a system, and this is going to be defined independently of the loads that are applied to the system. So in the same way we may have a cantilever beam and you put a force at the tip of the beam, you know that there are characteristics that tell you how that beam will deform. And it doesn't matter what the force or moment are that you apply on that beam. You know that the beam is defined by things like bending moment of inertia, Young's modulus, density. These are characteristics of the system that are independent of load. So modal analysis is the process whereby we identify the dynamic characteristic, which are the frequency, damping, and mode shapes of the system. Now structural dynamics is the study of how structures are going to respond when there are loads applied on the system. What we find is in many of the solution schemes that we use to determine the response, in one form or another, the modal characteristics of the structure are used for the response calculation and are very important for understanding how the structure behaves the way it does. So what I'd like to do right here is look at the time response of two systems. One is an animation on the left, and I'll start it up right now. It's really the response of a structure due to a random vibration input, but then there's also a vertical bump that's superimposed. So as we look at the displacement motion of this structure, we'll see that there are bending and twisting and torsion and side-to-side motion. And as we proceed through on this animation, right now we see mainly lower order deformation shapes, but as we get further along into the transient here, the response of the system due to the vertical bump, which is dominated by lower order modes, will start to die out because that's the transient response. But then the steady state or response of the system due to the random excitation will be broadband. And so now you'll start to see in some of the responses, you'll see a little bit of more than just the first bending mode or the first torsional mode of the system. You'll start to see some higher order modes, second order, third order modes in the response of the system. Now this is the physical response of the system due to the applied load. In order to really understand how this structure behaves, we need to understand the underlying dynamic characteristics defined by the frequencies and mode shapes to understand how much of the response is dominated by which particular structural dynamic characteristics. So if we see the response right now, you'll notice that you start to see some higher order modes, especially in the upper plate and the lower plate, and you'll see what looks like a traveling wave. It's really just a combination of many of the modes of the system, but there are higher order modes that are included in that response. Now in the structure on the right is a disk drive subjected to some displacement response, and right now I'll see that this is not recording properly. So what I'm going to do is I'm going to step forward, step back, and see if I can get that to start up. Well, that doesn't want to start up right now, and I've recorded this before, and so this is just the wonders of Windows helping me here. Well, let's proceed on, and we'll talk about the response of a simple plate. So let's say we had a structure that was freely supported. We apply a force at one corner of the structure, and we measure the response of the structure due to that applied force. Now the force that we're going to apply is going to be a sinusoidally varying force of unit amplitude, And the only thing I'm going to do is change the rate of oscillation of the input force. So I'll start from low frequency and then increase the frequency of oscillation, but I'm always going to keep 1 unit of amplitude input into the system. Now if we look at the time response in blue on the left, we'll see that as we sweep up in frequency, there'll be some frequency bands where the amplitude of the response will start to grow quite notably. But then we'll see that it grows a little bit and then it decays, and then it grows again and decays. So as we sweep up through the frequency range, we see large amplitude response at different frequencies of oscillation. Now if I were to take that time domain data and convert it to the frequency domain with the Fourier series transformation, what I'll see is that there are peaks that correspond to the frequencies where the time signal grew in amplitude. So if I looked at that, I'd say that each one of those peaks corresponds to a frequency where the rate of oscillation caused large time response in the blue response that we measured from the accelerometer. Now this is very useful information because these peaks correspond to the natural frequencies of this structural system. So at any time we excite the structure at one of these resonances, we will get large response. Now one measurement shows me a lot of information, but I'm still missing some information because I only know how one point moves and I don't know what the rest of the structure is doing. So if I were to proceed on and take many accelerometers and place them on the structure and measure all of them simultaneously, I'm going to run the same run we just made. I'm going to sweep from low frequency to high frequency, and all of a sudden you'll see we get to this large amplitude of response, and you'll see that the plate goes into a first bending mode. So as we sweep up through, we see large deformation, and then we start to see the decay of that measurement. So as we get up to higher frequency, we start to see less response. Now as we proceed on, we see that we get to the second frequency where we get large amplitude, and we see that the structure has basically a torsional mode of vibration. So at the first frequency where we had amplitude, it was a bending mode, and then we get to the second amplitude and it was more of a torsional, a twisting mode. And then as we go past that amplitude, we see it start to die down. And then we see an area where there's not much response. And then at the next two large amplitudes of response, we're going to see that the structure is going to have a frequency of vibration that's going to be the second bending mode and the second torsional mode. So at each one of these frequencies, the structure takes on a very unique displacement pattern depending on the frequency at which it is vibrated. Now remember, now we only put one force on the structure and we only kept unit amplitude. So I won't play this any longer. We'll go to the next slide and take a look at how the structure will respond if we were to put in a discrete sinusoid at each one of these resonant frequencies. But before I do that, let me just look at this one picture right here. And I'll notice that what I have is in the middle, I have an overlay of the time response in gray. Overlaid on top of that is the black frequency response function. And you'll see that I've specifically aligned this so that you can see that where the time amplitude grew, the rate of oscillation of that frequency corresponds to the first peak in that black frequency response function. And that at the point where in the time response the amplitude grows to maximum at that second region, we'll see that that's the rate of oscillation that corresponds to the second peak. The same is true for the third peak and the fourth peak. Now if I were to take my excitation device and dwell at one of those frequencies, so let's say at the first frequency where I have the line shown in blue, what would happen is if I measured all those accelerometer locations, I would see a displacement pattern in this plate that looked like a first bending mode. But if I were to take that excitation and put it at a different frequency, close to the second frequency of the system, then what I'm going to see is a first torsional mode of the system. And as I proceed on, you'll see that at mode 3 in green, I have a second bending mode. And at mode 4 in magenta, I have a second twisting mode of that system. Now what I'd like to do is look at this, but now I will try to look at the frequency and look at the animation of each of these particular frequencies, each of these resonant frequencies of the system. So at the first frequency, I see that I have a bending mode in the plate. At the second frequency, I see that I have a torsional mode of the plate. At the third frequency, I have a second bending mode. And at the fourth frequency, I have a second torsional mode. So you see each one of these frequencies causes a very unique displacement pattern in this plate structure. Now when we make analytical models, what we're really doing is we're taking a distribution of mass and stiffness, we're approximating that mass and stiffness, and most times we're using finite element models to do this. And then we do a solution scheme called an eigensolution to find the eigenvalues and eigenvectors. In other words, the characteristic frequencies and the characteristic mode shapes. So in this picture right here, I have the finite element model of a support structure for an engine mount. And each one of the frequencies, each one of the natural frequencies and natural modes of the system occur at a different frequency and have very specific displacement patterns associated with each one of those modes, just like the plate. The only difference here is the plate's a very simple structure, and this part of this automotive structure is a lot more complicated. But the same characteristic information is going to be there. So now what I want to do is talk a little bit about finite element modeling, why we do it. Well, basically, we use the computer to make our prototypes, if you would. You really use a mathematical prototype. The big advantage is that you can study many, many different variations of these models to determine what the best design might be. Now, some of the difficulties with finite element modeling is that you have modeling assumptions. How do you model regions of the structure? Is it plate-like or beam-like? Joints are difficult to model. They're not easy to model in structural dynamic modeling. Many times the interaction between components also becomes very, very difficult to determine. And another very critical item is damping. Damping is something that's very hard for us to include in the finite element model the same way we do it with design using mass and stiffness. We can assign some damping, but typically that has to be measured in order to be included into the model. But the same thing we do is we take this analytical model, we do an eigensolution on it, we basically decompose it into its dynamic characteristics, which is its frequency, damping, and mode shapes. Now these dynamic characteristics help us to better understand how the structure will deform when loads are applied, and will help us to make a better design. Now analytical models have a lot of assumptions. We always like to go out and test the structure to assure that our analytical model was a reasonable representation of the reality of the system. So with experimental testing, we're going to apply external forces, measure the response, determine the system characteristics from these measured functions. So the big advantage here is that we have actual measurements to find the system, and we can evaluate damping. The big problem with experimental modal testing is we have to have hardware. So you have to really build the hardware, and you want to make sure that you've made a reasonable attempt at getting a good model assembled with your finite element model so that you get a good prototype that has most of the design criteria that you feel is necessary for that particular configuration. Because now we're going to commit to hardware in order to have some prototypes. One issue that we have to face is sometimes boundary conditions may be difficult to simulate. Sometimes we model components or pieces of a structure, and unless we have the whole structure, we don't know how to really model these boundary conditions. Another very important issue is the fact that we test one prototype, and we have to make sure that that's representative of the real hardware that we're going to manufacture. Now with experimental testing, we have a variety of different ways that we can excite the structure to measure these frequency response functions Sometimes we use impact testing, sometimes we use shaker excitation, sometimes we use ambient loads. Sometimes our structures are very, very large, and it's not feasible for us to put in a forced excitation. Sometimes the structures are large, but we can put in some excitations and measure the responses. So there's a variety of ways that we could capture data, measure data, and extract modal parameters from that measured response function that we acquire. Now, I've mentioned these things called frequency response functions. What are they? Well, for this simple beam that we're going to look at, we're going to have 3 measurement points labeled 1, 2, 3, and we're going to measure possibly 3 places where forces can be applied to the system and 3 places where we measure response due to that force. Now, the functions that we measured are complex valued functions. These frequency responses have magnitude and phase, or I can express them in terms of real and imaginary parts. Now, we have a set of measurements that we can acquire. So I can put a force at point 1, measure response at point 1, 2, or 3. I can put a force at point 2 and measure response at point 1, 2, 3. And then also at point 3 and measure response at point 1, 2, 3. So in total I could measure 9 measurements here. And we tend to organize these things in a matrix sort of format so that we're thinking about rows and columns, output due to input. So we think row, column, output, input. Now let's look at one of these measurements. Let's say that we took an accelerometer and mounted it at the tip of the beam, and then we took a hammer and impacted the beam at the tip. So we would be measuring the response at point 3 due to an input at point 3. So the response function that we measure is H33. Now I only have shown the magnitude part of the frequency response function here. We have to remember that these are complex valued functions and they have magnitude and phase. So now I'm going to look at that measurement, and I'll notice that that is in the 3, 3 position of that frequency response matrix. Now if I were to impact point 2 and listen at point 1, listen at point 3, then I would have H32, the output at 3 due to an input at 2. And then if I were to impact at point 1 and listen at point 3, then I would measure H31, the output at point 3 due to an input at point 1. So I would be measuring the 3rd row of that frequency response matrix. So now let's take a look at that 3rd row of the frequency response matrix. Now one of the things I'm going to do here is I'm going to look at the imaginary part of the frequency response function. It turns out that the imaginary part of the frequency response function is a peak when the real part of the frequency response function is a 0. So what I'm going to do here is look at the magnitude of the imaginary part of the frequency response function. I'm going to look at measurement 3.1, 3.2, and 3.3. And if I looked at just mode 1, just the first natural frequency, the first peak, what I'm going to see is a deformation shape that looks like the first cantilevered bending mode of that beam. So that right away I get the impression that by just looking at the peak amplitude of the response, I have a sense of what the mode shape is, and I know what the frequency is because I know where the amplitude of the peak is in the frequency spectrum. Now what would happen if I looked at the 2nd row of the frequency response matrix? Well, I would be measuring the output at point 2 due to an input at point 1, 2, and 3. So I'd measure H21, H22, and H23. The output at 2 due to an input at 1, 2, and 3. Now if I measured the peak amplitude of the imaginary part of that set of frequency response functions, and if I looked at just mode 1, I'd see a peak growing. Well, again, this looks like the first cantilevered mode of the structure. The only difference I notice is that the overall peak amplitudes are lower in amplitude than they were in the previous case. I just stepped backwards for a second and looked at that measurement. You see that these measurements were larger when the amplitude was measured at point 3 than they are at point 2. So that tells me that somehow the location of the accelerometer that I use as a reference to measure these measurements is possibly very important to the total response of the system. Now what I'd like to do is proceed on and look at mode 2. Now if I looked at the lower two sets of plots in red, I'd notice that when the accelerometer is located at point 3, if I measured H31, H32, H33, and I looked at those peak amplitudes, I'd see that the displacement pattern looks like a second bending mode. Now that's when the reference accelerometer is at point 3. What happens when I put the reference accelerometer at point 2? Well, it turns out for this structure that point 2 is at the node of a mode. So if the amplitude of that mode is small or 0, then the contribution to the frequency response function will be 0. And that's exactly what I see in that last plot. We put the reference accelerometer at a point on the structure that corresponded to the node of that mode. So therefore we didn't see any response at any other frequencies. So it's very important for you to understand how this reference transducer can affect the results of your measured response functions. Now if I added some more measurements just to fill out the set of measurements that I have, I get a much clearer picture as to what the displacements are at each one of these modes. So what I've really done here is I've plotted the first mode in blue, the second mode in red, and the third mode in green. And what I have shown is the 3 measurements I had originally at degree of freedom 1, degree of freedom 2, and degree of freedom 3. And then I've filled extra measurements in. In this plot, we call this a waterfall plot, so that I can see the mode shape. Okay, now this works in one dimension, but it doesn't work very well when we have complicated systems. But the concept is what I want you to understand right here. So now we talked about having a test where we had an impact hammer that moved on the structure and we kept the accelerometer at the same location. Is there any difference when I have a shaker mounted on the structure and I move the accelerometers around and take measurements? Well, from a theoretical standpoint, there's no difference. If you looked at this matrix, you'd say, I can see this matrix has some symmetry. In other words, that the H31 is exactly the same as H13, and H23 is exactly the same as H32. So that since the measurements from a theoretical standpoint are essentially identical, then there would be no difference in the mode shapes whether we did a impact test or a shaker test. Of course, this is from a theoretical standpoint. There are some measurement issues that I might have to think of that might distort this a little bit. So now that I've talked about these measurements, these frequency response function measurements, well, where do they come from? Well, they come from my digital data acquisition system, and so I just want to talk about a few of the pieces of that system. We'll concentrate more on these as we go through more material. Well, the first thing that really happens is we have some excitation that causes some system response. Now we take this signal and we bring it into our digital data acquisition system, but the first thing I need to do is put an analog anti-aliasing filter to filter out high frequency information so it doesn't falsely present itself as a lower frequency component. The next thing I'm going to do is actually digitize the time signals. This is where the analog to digital converter does its work. Now, because of sampling issues that we'll talk about later on, there may be some issues that distort the measured function, referred to as leakage. So we may need to apply some kind of a weighting function called a window in order to minimize some of this distortion of these measured functions. Once I've come through to this point, the next thing I really want to do is take the Fourier transform of this measured data. So when I do that, what I'm going to do is get the FFT, the linear Fourier spectrum of the input and output signals. Now we never want to do anything with just one measurement, so we're going to take some averages here. And when we do that, we can talk about the average functions. So this set of measurements up to this point were for one record or one sample of data. Then what I'm going to do is then take another set of data, and these will average the auto and cross spectra for the measurement. Once I have these measured spectra, then I can go and compute the frequency response function and the coherence. So now when I go to take these measurements, is there anything that I need to be concerned about when I do an impact test or a shaker test? Well, there's many things we're going to talk about, but if I had to pick two things, one of them is definitely going to be how do you select the hammer tip to excite the structure. The harder the tip, the broader the frequency range of modes that are excited. The softer the tip, the narrower the range. So there's got to be some balancing act here where I pick just the right impact hammer force so that I excite the modes of interest without exciting other modes that are not of interest. I also have to make sure that I have enough energy to excite the modes that I'm interested in measuring. Now in this upper trace you'll see that there's a blue force spectrum, an input spectrum, which has significant energy during the first third to half of this spectrum. But after that, the input power spectrum drops off rapidly. If there is no input force, there won't be any response. If there's not any response, then the coherence will say that not all the output was linearly related to the measured input. If I look at the lower trace, you'll see that we did a much better job in picking an excitation that did a nice job of exciting the frequency band of interest. You'll see that the input power spectrum is reasonably flat, the frequency response function looks fairly good, and the coherence looks fairly good. So we'll talk more about these kinds of measurements as we go on. Another thing that's very important, as we talked about leakage and windows weighting functions, many times when we have impulsive loads, we have damped exponential response of the system. In lightly damped systems, this response might ring on and on and on, making it a signal that's not totally observed within one sample interval of the spectrum analyzer, and then leakage will occur. In order to minimize this, what we need to do is somehow process the data to minimize this leakage phenomena. One way to do it is by adding windows, and the window that we would add is called an exponential weighting function. So these can sometimes distort data, and we'll see a couple data cases where too much damping was used and it was very hard to really figure out what the modes of the system were. Well, that has to do with impact testing. What about with shaker testing? Well, there's lots of things we can talk about in terms of shaker testing. But right now, let's just say that there's a variety of different excitations that we can use that are useful techniques to acquire good response functions. And we'll talk about these in a lot of detail. These are really excitation techniques. We want to try to measure the best possible frequency response functions we can. So how do I get these mode shapes from these frequency response functions? Well, previously we've talked about this plate structure, and if I looked at this particular set of measurements here, you'll see that I have just two modes in the frequency band of interest, mode 1 and mode 2. And you'll see for the first mode, I have 6 measurement points on this plate structure in blue. You'll see there's 2 at one end of the structure, 2 at the other end of the structure, and 2 in the middle of the structure. Well, if I looked at these response functions, and if I looked at the peak of the imaginary part of the frequency response function, I'll notice for the first 2 measurements there's a -1 unit and -1 unit at the left end of the plate. So now I'm just looking just at the first peak for mode 1. And if I looked at the 0.5 and 6 on this plate, and if I looked at the peak of mode 1, I'll see that they're also -1 unit. But what I will notice is when I look at 0.3 and 4 on the structure, you'll see that the amplitude is +1 unit for both of these locations. So what this implies is that the 2 ends of the structure are going down while the middle is going up. Now with just those measurements, I have a pretty good idea that this might be a bending mode of the system, and if I took more measurements, I would confirm that. So this is a very quick and dirty way for us to get a feel for what the displacement pattern is at a particular frequency. Now for the second mode, shown in red, now I'm just going to look at the second peak at this point. We'll see that the first measurement point, the peak amplitude is +2 units, but the other point now doesn't move in unison. It moves out of phase, so it has -2 units. If I look at the other end of the structure, I'll see that point 5 has a -2 units and point 6 has +2 units. And then further, what I'm going to notice is if I look at point 3 and 4, I'll notice that this is the node of the second mode. It's a point of 0 displacement, therefore there's no response amplitude in the frequency response function. So again, if I plot these amplitudes, I'd see that there's a twisting across the plate. So this is a very big distinction between mode 1 and mode 2. Mode 1 is bending and mode 2 is twisting. And I need to understand these shapes if I'm going to design hardware. So how do I get these mode shapes from frequency responses? Well, we talked about this in a very simplistic fashion, but what I really need to understand, and modal theory will tell me, is that each of these frequency response functions is made up of the response of a set of single degree of freedom systems. One for mode 1, one for mode 2, one for mode 3, and so on. So the response function I've shown here in the black is really the linear combination of the response of the system due to the effects of all the modes of the system. What I have in the lower plot is the mathematical decomposition of that measured function, trying to tell me how this response function is controlled by certain frequencies and certain mode shapes of the system. Now, originally we did this by just picking peaks. Well, that's a very simplistic approach. And really what we want to do is apply some mathematical methods to this. But as I look at it, I'll notice that at the first peak, well, there's basically a single mode and there's not much interaction with the other modes of the system. But when I get to mode 2 and mode 3, I'm going to notice that the modes are very, very close to each other. So what I do is I use mathematical routines to help me decompose these measurements into the basic parameters that make up these response functions. And so we'll talk about modal parameter estimation extensively in this course, and we'll see that it's a tool that we use in order to extract parameters of the system. So how do structures vibrate then? Well, I think we're starting to get a little bit of a picture here. If I looked at the upper traces and I see that there's some time force applied to the system, causes some output time response. Well, looking at these two time plots really doesn't really tell me a lot. It says, yes, I put some input in, yes, I got some output out. But if I asked you what frequency of the structure was most excited by the excitation, what's the spectrum, or what's the frequency content of my signals, you really don't have any idea. Now, by taking a look at the data and transforming it to the frequency domain, I start to see things in a different light. Things start to become a little bit clearer. For instance, if I look at the lower plot here, this input spectrum, I'll see that now that I took this time data and transformed it to a spectrum, I start to see that there's some energy that's distributed over the frequency spectrum, and I understand a little bit clearer what energy content exists at what frequencies. Now, the frequency response function is really multiplied by the input force spectrum to cause the response. Now, this frequency response function, mode 1, mode 2, mode 3, mode 4, help to dominate or determine where these peak amplitudes are. So that I see that there's a first mode, second mode, third mode, and fourth mode. First mode's bending, second mode is torsion. So if I look at the energy and I look at the power or frequency spectrum that excites the first mode, I know how much of that time force response is going to cause the first mode to respond, and how much of that time force in the frequency domain is going to cause the second mode to respond, and the third mode, and the fourth mode. So the frequency response function becomes a very important parameter for me to understand how the input signal is amplified and attenuated on a frequency basis. This causes this output spectrum. Now in this output spectrum, you'll notice that some of the peaks are a lot larger than others. I would have never surmised that from the time output response. But here I can see that the first mode is almost hardly excited at all, and the second mode's excited a little bit. The third and fourth modes are excited quite a bit. That's because the input force spectrum has more energy at higher frequencies than it does at lower frequencies. So now I can understand what the time response is and what causes that response in the system. Now we've talked about frequency response functions, but a very popular way to collect data is something called operating data. We have some structure and it's in some operating condition, there's some loads applied to it in a particular configuration, and the structure deforms. And so we make dynamic measurements. And so we collect what's called operating data. Now when I do that, sometimes I see deformation patterns and they just don't make physical sense to me right away. And so I say, is it possible for the structure to actually move like that? So let's look at this a little bit more closely. Let's say that I had a sinusoidal excitation that was right at the first resonant frequency of the system. Well, then what's going to happen is I'm going to measure an operating deformation shape, and since I'm close to the resonant frequency or right at the resonant frequency, I'm going to see a deformation pattern that's highly dominated by the first mode of that system. Now that's not to say that the second mode doesn't have any contribution, it's just that its contribution is so small it's overpowered by the first mode. And we can see that in the time response. You'll see the blue sinusoidal time response is a lot larger than the red time sinusoidal response. So that the contribution of the total response of the displacement of the system is heavily dominated by the first mode of the system. The second mode has very little response. Now if we were to take that excitation and move it to the second frequency, because the torsion is then going to dominate the system. So I see here that I see a large amplitude response of the second mode, very little response from the first mode. So I see primarily a torsional mode. Well, what would happen if I happened to have a dwelling frequency that was halfway between the two modes? What would I see? Well, I'd see a little bit of a contribution of the first mode plus a little bit of a contribution of the second mode, and they'd be added together in some linear combination. So if I looked at that magenta curve again and I looked at it close enough, I say, gee, part of it looks like it's bending, but part of it looks like it's twisting. And so maybe I could get that deformation because I have the linear combination of the bending mode and the torsional mode. Neither one of them are excited at resonance, but they have a characteristic shape, and therefore what happens is the total response of the system is made up of the linear combination of the pieces. So now I can look at operating data a little bit further. In operating data, we never have the frequency response function or the input spectrum. We only measure the output power spectrum. So if I were to do that, I'd look at that measurement and say, boy, I can see the output, but I really don't know what caused it. But we now understand that that frequency response function, which is nothing more than the sum of a bunch of single degree of freedom systems, is excited by some input spectrum force, which is whatever the measured excitation is. We don't measure it. It's operating data. We don't know what it is. We just say that here is the response. But we know that that response has to be controlled by the frequency response of the system. So we could go back and look at this operating data again. I won't play this time domain animation again. We saw it before. we can see how the system responds. It's nothing more than the linear combination of the effects of many modes of the system. So what good is modal analysis? Well, modal analysis is the process whereby we define the dynamic characteristics of the system. What we can use this data for is we could do something called structural modifications. We could say, what would happen if I added a rib to the system? What would happen if I added a mass to the system? How does that change the frequencies and mode shapes? How does that change the response of the system? So that's a very, very useful tool when we're trying to understand how to modify a system. Right? So we have these modal characteristics, and it doesn't matter whether it comes from a finite element model or from a testing model. I can study the effects of changes of system characteristics and how that affects the performance of the system without having to build the actual changes. So we're going to study this to understand what's the best way to modify the system before we build it. So if we said, what good is modal analysis? Well, one of the ways we use it is really for simulation, predictions, correlations. These are a variety of ways that we use this. So it could be that we start either from the testing aspects of frequency response functions and parameter estimation and get modal parameters, or from a finite element model where we do an eigensolution and get modal parameters. So we may do some correlation of the model and then maybe do some adjustments to the model. The end result is that I'm going to develop the dynamic modal model, and that dynamic modal model can be used for structural modification, correlations, simulations, predictions, and we can use real-world forces to predict what the response of the system will be, and if we don't like the response, then we can go back and make some structural changes and continue this in a loop until we converge on a solution that makes sense for whatever it is we're trying to determine. So the big question that really always comes up is, should I collect modal data or operating data? Well, I always want to have both sets of data, but if push comes to shove, I'm probably going to start with operating data first, because that's where my problems occur. I see some data, I look at how the structure is deforming. Sometimes it becomes an easy problem. You'll say you have a rotating unbalance, and it might be close to one of the structural resonances. You measure the operating data, and you say, yeah, okay, sure, that's the third bending mode of the system, and here's how we're going to modify the system. But sometimes the operating data is confusing, and it's not clear-cut as to which mode or modes are primarily causing the total response problem for your system. In those cases, then I want to collect modal data in addition to the operating data, so I have a better understanding of what the modes are, so that I can then make some structural changes or fixes to the system.